let's talk about the Maxwell's wave equations. So specifically, I'm going to be talking about the inhomogeneous electromagnetic wave equations, and it is one of the equations describing the propagation of the electromagnetic waves. They're generated by a non-zero source charge and currents, and that is why inhomogeneous. So later on we can substitute for charge and J, current density, to be equal to 0, and therefore we can reduce it to a homogeneous problem. So the equations are going to follow from the Maxwell's equations. These Maxwell's equations I'll write down here in SI units. So I'm going to be first writing Maxwell's equations first, right? So the Maxwell's equations of electromagnetism are as follows. So del dot E is equal to rho, the charge density, over epsilon naught. The next equation is the gradient of the magnetic field, which is 0. Then we have the curl of electric field, which is equal to the negative time derivative of my magnetic field, right? And at last we have the curl of my magnetic field, which is equal to mu naught J plus mu naught epsilon naught and the partial time derivative of my electric field. Right. Now I'll use the fact that my mu naught epsilon naught is equal to 1 over c squared, right? So once I do that, then I can write my curl of B as mu naught J plus 1 over c squared time derivative of my electric field E. Right. So now let's move on to the derivation of the Maxwell's wave equations. And the derivation is quite simple, though it might look a bit crazy. I promise you that it's going to be really simple. So let's move on to the next page. And now I'm going to be using a result from vector calculus. So I'll write here that recall from vector calculus that I have the curl of my some vector field V is equal to del on the divergence of my field V minus the Laplacian of my field V, right? So using this result from vector calculus, I can then easily find the Maxwell's wave equations. So let's first apply this curl of curl on V, and suppose that V is going to be my electric field E. So that is that first I'll be deriving the Maxwell's wave equation for electric field, right? So let's go ahead and do that. So curl of my field E is equal to then del of divergence on E minus Laplacian of E, right? So, well, all of this is then going to be equal to the negative curl of my time derivative of B, right? This simply comes from the fact that I have over here my Maxwell's equation curl of E as this, right? So I have simply taken another curl of E. So I have then obviously I'll have to apply that curl on this right hand side as well. So that's what I have done over here, right? Okay, so the next step is then that we are doing all of this in our Euclidean space, that is or a flat space-time, right? So the partial derivatives will commute, and therefore we can switch the positions of these two, right? And so if we can do it, I am going to do it, and we will then write the equation as following. Everything is going to be same except for the position of my partial derivatives on the right hand side. So del gradient of E, it's getting a bit messy, so from next equation or expression I'm not going to write these vector signs, and I'll assume that you already know what is a vector and what is a scalar, right? Okay, so negative Laplacian of my E, all of this will then be equal to, let's get rid of this thing over here. Okay, so all of this will then be equal to negative partial time derivative of curl of B, right? Okay, so from now on I'm not going to be writing these vector signs on top of the vector quantities, and like I said, I'm going to assume that you know the difference between a vector and a scalar if you're watching this video. Alright, so let's move on and substitute the value of this curl of B, because we already know what that is from our Maxwell's equations. And so let's say that now this thing over here will be del divergence of E minus the Laplacian E is equal to negative time derivative, partial time derivative of my, I'm substituting the value of curl of B over here. So what is that? That is mu naught J plus 1 over C squared times the partial time derivative of E. Right. Okay. Now we can simplify this a bit more, because of course we know the value of our del dot E, and so let's substitute that in this, and therefore what this equation goes on to become is 1 over epsilon is just a constant, I can take it out, then del of rho, the charge density, right, minus the Laplacian of my electric field E, that is from here, and all of this will then be equal to negative mu naught, it's just a constant, so let's take it out, partial time derivative will apply on J, so partial time derivative on the charge density minus 1 over C squared, and we'll have the partial squared time derivative on E, right? So all I've done is I've distributed this time derivative over here to both of these quantities over here, right? Okay, let me get rid of those lines. All right, so what is the next step now? The next step is to simply move these equations. I'm going to move this equation, I'm going to play with it, and I'm going to write it in another representation, which I'll do it on the next page. So the above equation can now be written in this form, that my Laplacian of E minus 1 over c squared times the partial time derivative, the square of that, or operated 2 times on E, is then equal to 1 over epsilon naught del rho plus mu naught time derivative, partial time derivative of my current density, charge density. This is J is the current density. So if before I said J as charge density, I'm sorry, that's my rho, right? All right, so now if you have watched from my previous videos, my previous video on the Klein-Gordon equation, there I had defined an operator that was the D'Alembert operator using the 4-vector formalism, right? So when I did that, I got this thing over here, that my D'Alembert operator is Laplacian minus 1 over c squared partial squared, or the time derivative operated twice, right? So if you remember this over here and you note this equation over here, we can use the D'Alembert operator, and in this equation that I have drawn with an arrow over here, right? So when I do that, what do I get? You see, my D'Alembert operator is Laplacian square minus 1 over c squared partial squared time derivative. So I can see something similar in this equation over here, right? So I'll just substitute for D'Alembert and I'll get D'Alembert operator on E is equal to 1 over epsilon naught del of rho plus mu naught partial time derivative of my current density J. Or I said I'll not be using the vector signs, so let's remove that. Alright, so this equation over here is one of my Maxwell's wave equations, right, for electric field E, right? Okay, so now you can substitute for charge density this thing and current density as being equal to 0 for a free space, and so for the free space then you could get your Maxwell wave equation for electric field as this term will be 0, first term over here will be 0, this term over here will be 0, so equal to 0. So this is your Maxwell wave equation for electric field for a free space, right? Okay, so let's go ahead and now do the same thing for the magnetic field, but for the magnetic field it will be very easy because we know that the gradient of the magnetic field vanishes, or it is equal to 0. So for that we will not have to compute this quantity over here and it will vanish. So all we have to do is compute the Laplacian of our magnetic field, right? Okay, so let's go ahead and do that here. Right, so now we'll be using the same identity from vector calculus that I mentioned before. So curl of my vector field, that is my magnetic field in this case, right? And this is then again going to be equal to del divergence of B minus the Laplacian of B, right? So now we know that my divergence of B, this term over here, is 0, so I can just cross this term out, and so I'll be left with only this term over here. So let's write that down. This will then become mu naught. Now this thing I'm writing over here after the equal to sign is simply the curl of my B, right? So let's write it down as mu naught curl of J plus 1 over C squared curl of my electric field time derivative, right? Let me get rid of these vector signs because I said I'll not be using them, so you might get confused. Alright. Okay, so what can we do now to this equation? Well, we can write it down as negative Laplacian of B magnetic field is equal to mu naught curl of my current density, and now I'll have my curl of E over here. Now I did not mention this above because I did it before, but let me say it again, that this thing over here, I can switch the position of my derivatives, partial derivatives, so I can write this term over here as my partial time derivative curl of E, right? Okay, so if I can do that, then over downstairs I'll have this thing over here as negative 1 over C squared, right, times the partial time derivative operated 2 times on my magnetic field B. I have simply written here the value of my curl of E, right? Okay, so well, we're almost done now. So let's write this equation down like this, that you have Laplacian of B is equal to 1 over C squared partial time derivative operated 2 times on B is equal to mu naught curl of J. And we are done over here. Let's just write this down in terms of the D'Alembert operator. So that will be B is equal to mu naught curl of my J, right? Let's get rid of this vector symbol. I'm used to writing this vector symbol on vector quantities, but it might get clustered over here or cluttered over here. I don't know the right word, so I'm not writing those, right? Okay, so this is our second Maxwell's wave equation for magnetic field, right? And again, if I have this in my free space, this equation shall become like this, right? So my current density vanishes. Alright, so we are pretty much done. This over here is my first Maxwell wave equation, and this over here is my second Maxwell wave equation. So for the pleasure of it, let's write both of them over here. So that will be for my electric field, it's this thing over here plus mu naught time derivative of my current density, and the second equation is for the magnetic field is this thing over here, mu naught curl of my current density. So these are my Maxwell's wave equations, or specifically my inhomogeneous Maxwell's wave equations. Right, okay, so now they have solutions, and the solutions to the inhomogeneous electromagnetic wave equations, that are these equations over here, is something like, suppose there is absolutely no boundary around the source, right? And in such a case, the solutions are then written or described something like this. Okay, so I'm first going to write the solution for my scalar field, which I'm going to represent it with psi, right? So psi r, here note that this r over here is a vector, but let's not write the symbol for the vector over there. So rt is equal to the Dirac delta function t prime plus this thing over here, or the absolute value of r minus r prime minus t, all of this over absolute value of r vector minus r prime vector, and on this side I have my charge density that is going to depend on my r prime and t, but because I don't have further space, so I'm not going to write that it's going to depend on what, but it's going, this rho is dependent on r prime and t, right? And so the integration is over d3 r prime and my time dt prime, right? Okay, all right, so this over here is the scalar solution, the scalar potential solution, and these solutions are called, they have a name for them, but let's write down the vector potential solution, right? And then we shall go to what they're called, right? Okay, so I don't have space over there, so I'm going to move on to the next page, and here I will write my vector potential solution. So that is A, and this is going to be a vector, right? So R, which is again also going to be a vector, T, it's a scalar, right, is equal to the integral, again I'll have my Dirac delta function t prime plus the absolute value of r minus r prime over c minus t, and I think I should have left some space over there, so that's minus t, all of this thing over r minus r prime, the absolute value, and then I have over here my current density J that is going to depend on r prime and t prime, right, over C, and the integral is over my space and time, so dr prime dt. Alright, so this over here and this over here, these are my solutions to the Maxwell's inhomogeneous wave equations, right? And these solutions are so important that they deserve a name, right? and they are so known as the retarded Lorentz gauge potentials. Now, they're important, right? They're important because they represent a superposition of spherical light waves that are traveling outwards from the source, from present into the future, right? Okay, so now I said some words, right? I said that they'll be traveling from the present to the future, right? So could there be solutions that represent this traveling from future to present, right? Or maybe present to some past, right? So think about that, and I shall leave you with this for this video. Good luck and thank you.